That's all just stopped. That's good. What have we done? It's all just stopped.
Did that before, I don't know why.
Well, I know.
Right. There's the Raspberry Pi there, with the prototype board sat on top, which is the middle picture. And on the prototype board, a 3.3 volt regulator, and it's got its own 5 volt power supply. It repeats the GPIO sockets. And this chip here is an I2C repeater, and there's I2C ports there, and there's one connected already into the I2C highway.
It's lost a picture of the back again.
Yeah.
Alright, till you mess about then.
Yeah, alright, back.
Right, and then I brought the rest of the GPIO ports out on that socket there, and it's got resistors and diodes in to protect the inputs, because Mike Cook's going to have to do it. So. And then the black socket on the end is a repeat of the first 10 pins of the Raspberry Pi socket. And then on top of that, there's this little real-time clock chip, which sits on top as well, because this one doesn't go on the internet much, this one, so it's got a real-time clock with a battery stuck in the side of it there. Let's take the glass.
Is that the CJE's?
Yes, yeah. It's actually got a thermometer in it as well. But, Right, those are the socket of the Raspberry Pi, telling you what the pins do. First two are power, and then the blue ones are the I2C highway. Then you've got a ground, and then you've got yellow ones which each says a transmit and receive serial port. And then the GPI4 there onwards, you can make those become whatever you want. And I found a module which you can adjust the GPIOs. And if you can see around the black, they're predetermined, because those have been made, the serial port and the I2C port. The red ones are inputs. So it shows the state of the inputs. But if you could click the menu over this, it tells you it's an input. If you click adjust on it, the background goes green and it makes it an output. And it tells you that's GPI4 and it's now an output. If you click the select on it, it will turn it on. And if you plug in some LEDs, click select on it, it will light up the LED for that GPIO. So we click the adjust on these, you can turn them all on. And off, etc. So if you click the menu over, it will tell you the pin number, it's GPI 25 and it's an input. It comes with help, because it's actually a common program for Beagle boards as well as Raspberry Pis. If you click on the Raspberry Pi bit, you've got the SWI that calls to do the work. So you can read the state of pins, you can write to the state of the pins, and you can change the inputs and outputs. You can read the state of the output, whether it's an input or output, and you can write as an input or output. The ones that are surrounded with black are actually pre-allocated to be something else, a type 0. So it's not a GPIO anymore, it's been allocated to be, in that case, it's a I2C highway. There's mention here of this chip here, the MCP23017, which is that one there, which is an expander chip. Which just looks like that. And it connects to the I2C highway, so there's 2 pins and power. If you click the adjust on the icon bar, you now get an extra 16 pins to play with. And again, you can make these inputs or outputs by the adjust button and select them to turn that LED on. Put that one into there now. So you can play with these as well. That's going via the I2C highway, but you can still get at them. Write your own little basic programs, and using these calls, GPI read data and write output.
Just lost it again.
Coming back. There it is.
It's when you stand up, it'll go back on again. Annoying.
So yeah, using these SWI calls, you can then write your own programs to make inputs and outputs, whatever. So if we run that program, we should have put it on, and you can turn it off. Right. You can have more than, you can have up to 8 of these on the I2C highway, because they've all got address chips, which are the ones down there. There's 3 binary address chips that you can put the links in and out, so you can have up to 8 of these on the highway. So that's an awful lot of ports if you want to play with. If you want to drive some motors, it's the same drive chip. You've got a stepper motor and a servo. So it's a 4-phase stepper motor, so you need 4 GPIO pins to make it move. We've got the driver chip, which is just an open collector chip, and that stepper motor needs 12 volts, so we'll put some 12 volts into it. The servo just needs 1 pin to drive it, and then the minimum position on the servo is half a millisecond pulse width. When it's in the centre, it's a millisecond pulse width, and then the maximum is 1.5 milliseconds, and that's repeated every 20 milliseconds, which is how the servo works. Right, so if we run this little program, it comes down, and you can adjust the servo. and the stepper motors. You can make it take steps. Just by cycling through the 4 phases, it will step. That's what it's taking one step at a time. So you can do things like that with it. Just with the 4 GPIOs for the stepper motor and 1 GPIO for the servo. That's using the Y calls on this module. Right, we've mentioned the serial port. I've been wanting to get a serial port working on the Raspberry Pi ever since I've had it, because most of my stuff needs a serial port. And whilst on their rules site, I actually found a module.
Gone again.
It has gone again. They've just gone back. Give it to them. I sometimes wonder if it's a way to the cables.
I think you just get bored.
Well, they're not a push lock connector, are they? Just something like, you know.
We should stop it auto seeking the inputs.
You can't, it's the way they design the thing and things. Yeah. Oh, let's do it again. There you go. Let's try something.
I swapped the cable. So.
Try a bit of deviosity. No. And the weight of itself will pull itself out.
Saying confidently.
You have to try and sound confident.
Right. So it says you can set the speed, and there's a list of speeds there with this module. And
Okay, there you go. That's that theory gone.
Just get bored.
I think it does, yeah. So it's got the attention span of a 10-year-old.
It will
With a mobile phone, yeah.
It will cycle back eventually.
Yeah.
you can set the format, stop bits and start bits. You can write to it, write data to it. And there's all sorts of other things. So I made an adapter to plug in, which is that there, which is this picture on the screen. There's the 10 pins there. Let's say it's the first 10 pins that are repeated on that black socket. So there's power, the I2C highway, and the transmit and receive. And there's a serial driver chip, a UART chip, and there's actually an I2C on here, so I can test the state of the leads on the serial port. And that's the circuit for it.
We'll be in a second.
Just ignore it.
Yeah.
Grief.
Right, this is the Raspberry Pi side, and that's the pin number 1 for 3.3 volts, which is that orange one.
What it is, it's 'cause it's got 2 leads, one of which isn't connected.
Well, I swapped them
Yeah.
to try and...
But it'll be seat. It knows there's nothing on it, so it'll go looking to find nothing. But yeah, daft enough to do that.
So pin 8, because that's pin 2 there, 2, 4, 6, 8 is the transmit, 10 is the receive, and then on the other side there's the I2C highway connected to this chip. The serial driver chip has got 2 transmitters and 2 receivers, and it's got a voltage generator in it because the serial port needs plus and minus 7 volts, so it's actually got a voltage generator in the chip as well. So from the 3.3 of the Raspberry Pi power, it generates plus 7 and minus 7. So the outputs will swing from plus to minus. Right, the extra pins are going by the I2C highway chip, and I put some transistors in for the bits that there's only 2 spare drivers on the chip.
Still not looking for it. How much were all 3 chips together? Any idea?
No, no, but not that much. Only 10 quid,
something like that?
if that.
Yeah.
Right. It's got a little terminal program here using that chip, and in the white box there's a microcontroller with a serial port on it, which is there. So to connect the other end to the Raspberry Pi adapter. Right, put the menu up like they're all ticked, so it's all the signals are there. It's set the baud rate and the protocol. There's a bit of a program in there, a terminal program, so if I put a command in with a bit of luck, it should identify itself. It's not behaving. That's better. Right, those are the commands that are available on that little white box. It's a microchip device that's in there, and it's got a serial port. As you can see, it's got GPIO ports, analog ports in that chip. Around the program, there's a read command there, so I can remote read memory slots, the memory slot of the microcontroller. If I read 6, it reads memory slot 6. No, it's not. It's done it there. It's actually produced 07. I read memory slot 6, which is actually the display that's visible on there. So the 0 is the 0 of the display. The 7 are actually the buttons, the state of the buttons. So it's reading the GPIO memory slot. So I can then write to it as well. And it's 6. The memory is 6, and if I make that 17, with a bit of luck, that should have changed. So I can write to the memory slot as well, which actually appears as a GPIO.
Right. I wish you could write to rejected.
I can change it to 2 or whatever you want to write to there. Or put it out. Right, that's using these serial port calls to transmit and receive data. If I turn that off with a tick, nothing happens. If I turn that one off, and still nothing happens. It should have returned with the receiver turned off, but anyway, it's not having it. Right, don't forget that then.
That's demonstrations.
Yeah, easy to unplug it as well, in the safest way. Yeah, and then it's all turned off. It's disappeared because it's unplugged. So that's using the I2C highway chip to read the state of the pins. It's back again. Right. notice on the bottom of the baud rate one, it says it does 31.250 baud, which is actually the MIDI speed, MIDI music interface speed. And that's actually 1 megahertz divided by 32, which is why we've used it, because it's easier to generate than these odd baud rate numbers. Right, so it says it does MIDI, so we'll build an interface and see what happens. Right. Well, there we have the MIDI interface. There's a picture on the screen again. It plugs in the same highway, the first 10 pins, and its DIN plugs in and out. So I'm using the transmit pin again through a driver, and actually I've produced 2 outputs on that. Acorn decided to have 4 sockets, but you only really need 3, so there's always been 2 outputs on Acorn ones. The driver chip is just a standard TTL chip, and the little chip is an optically isolated chip, because the MIDI interface is optically isolated so that you don't get mains coming. So the receiver part of the device has this little chip which has got an LED and an opto transistor inside the chip. So therefore there's no electrical connection at one side to the other. And it's a 5-pin DIN plug that connects. You're only using two leads in it. So there's power, there's +5 going through there and on out. That will go to the MIDI, the other box on the receiver end and the other end, through the LED and back to the 5, to the driver chip. So you've got a DC path right the way through. The other bit on the MIDI is you've normally got a through, because you can chain these devices one to another. So if you're on the receiving side, it goes through another driver, pair of drivers, and out on the through output, so you can chain the devices. So that's a MIDI cable, and on the end of there there's a music box which generates sound. So if we plug that into there, again you can write a little program, a basic program, to set the port up to 31.25k baud. With that command, you need 8-bit for one stop, which is that. There's a buffer that you can set with these sway coils, so you can set up the buffer. We're purging the buffer. Right. A bit more about MIDI. This is Acorn's MIDI manual. We'll go into the specification. The first byte that's sent always has bit 7 set, and it's broken down into these signals. So if high bit of 8 is note off, high bit of 9 is note on. The N is the channel number, because you can down one MIDI cable, you can control up to 16 different voices. So you're not limited to one voice per cable, you can control 16 by having the channel number where the end is. So I've got note off, note on, and there's another 2 bytes following that, neither of which has bit 7 set. The first one is the note you want to play, so you've got 127, 128 possible notes that you could play, and then the third byte is the loudness that you want to play it in these 2 commands, although it's normally, if you play a note off, it's always 0 is the last byte. You've got another one here. A is the channel pressure, so you can adjust the loudness of the note you played. Like if you're playing a trumpet, or you can play harder and it gets louder, it simulates that for the particular instrument you're playing. I'm not sure, I can't remember what control it does. It does, right, it does various things. It's all sorts of odd bits and pieces in there. This one is the more important one. C is a program change, and that is telling it what instrument you want to play on that channel. So there's C, the channel number, and then 1 extra byte. So you can have 128 possible different instruments that you can set that channel to be. D is the pressure. So that's equivalent to the sustain key on a piano, where it controls all the voices. E is bend, pitch bend. So as if you're bending a string of guitar, you can simulate that. Now I'm going through the rest. It's too complicated. Right. So if we look at this, I'm sending the C note because it's channel note. It's a C. I want to change it to voice number 1. So I'm putting those in the buffer, and then I'm going to send them. Then I'm going to play a note, which is 90, note on. The note I want to play, which is 60, and the loudness 64. And then I'm going to turn it off. Same thing again, but with 0. We don't need the projector for this bit. If I run that program, we should make a noise of a piano.
The symphony will take a little longer.
Yeah, it's a bit more complicated program than that.
So I think it proves that you can do it in BASIC, just to test things. We do have a little music program, just as a demo. So if I drag a tune into here, and start playing it, it should make some noise. You can see that that's playing multiple voices. Right.
What program are you using for that one?
It's one I wrote myself. It's only a demonstration, it doesn't work that well. It's basic and it's not multitasking either, it is basic. Because I haven't found one that will work with this module yet.
Right.
And be 32-bit as well. Right. These standard MIDI music files that have been used forever. I've got a header, MT HD, so you know it's a MIDI file, even though it doesn't have a file type of MIDI. You don't really need it because it's got that header in it. The next bit is the, let's have a look what's in there, is the file type, whether it's a multiple file or you can put all the voices in one file. So that's the MIDI type. There's a time signature, which in this case is, no, that's beats. And then there's a, you can work it out from that 192, which is the beats per minute figure. So it knows how fast to play it. Right, and then after that there's an MTRK track. That's the start of the first track. And when I've dragged it into this screen, you can possibly see that it's pulled out the synth string. So it's identified this track as being a synth string, which is appeared in the window. And so there's a lot of spaces after that, and then there's actually a C1, so it's telling it that what instrument to be. And then the next bit is a delay, because you need, with it being a file and not playing live, you need to know how long to delay before the next action, which may be a note being played or turning on and off. So the extra bit in this file, other than the MIDI information, is just the time. So that's all that's in there. The instruments plus time. Right. You might notice again on the bottom line there, it says it does MIDI and it says it does DMX. DMX is light controllers. It's a similar thing to MIDI but for lights. So again, I'll build a little interface to see if it will work. Which is there. This is our first prototype. And right. So then I'm just using the transmit in this case. It's 250k baud rate, 8-bit 2-stop bits, no parity is the format. And the 250k baud rate is 4 MHz divided by 16, so again it's easy to produce that baud rate. So the transmit goes through some gates because I need to force a break out on this driver. So I'm actually using the GPI 4 pin to force a break, because break is used to signal the start of a light sequence. And then there's a line driver chip, which is the little chip. And on this one, the little orange socket at the top is where the DMX socket would have plugged in. So there's a line driver there, which is a balance driver. It's the same format as the old Ethernet on the BBC used to be. It's a twisted pair, and you can chain them up, and the last one's got a terminator in. Right.
Not those longer runs until the MIDI's got a limited length, hasn't it?
Without repeaters.
Yeah, whereas DMX I think goes.
It doesn't have that much longer run really, but
no.
Again there's repeats, you can have repeaters on that as well. Right, so that To start the transmission sequence is a break signal for 1 byte's width, then there's a gap of a byte. Then you start transmitting the data, and you can transmit up to 512 bytes after that, which are the lamp brightnesses. So you can control 512 lights. You don't have to send all that because the break signals that you're going to start again. So you can send as many as you want, really. Right, it's supposed to be a 5-pin. The current specification says 5-pin, but all the ones I've ever seen have been 3-pin, just to confuse it. So it doesn't seem to follow the specification that well. Right. Somewhere on there, there's a DMX. There we go. It's an XLR, 3-pin. The problem is when I try to use this, it hangs the PC. The Raspberry Pi hangs when you start to throw data at it down the serial port, and it is just the serial port that it hangs on. So there's something wrong with that driver, unfortunately. But if it was working, then what should happen is it should light lights. Which you control. Let's say we're sending out brightnesses of the lights. If I just reset the baud rate on this thing. Cheat by because that's got a serial port. Put the serial port back in. So I can then control the light brightnesses by clicking on here. Like so. Right, I've got some sequences in here which we can drop on. Drop the settings on, then it'll tell me what colours the lamps are. If I drop a file in there, it should start to flash the lights a bit. The box over there has got an in and an out, so you can chain them, devices, because that's only got 4 lights on it. So as I said, you can control up to 512. So you need really more boxes. And on the DMX, you'll see that there's some little dip switches on the front of that. So you can make that box appear as any of the light sequences. So it's at the moment it's set to 0, so it's lamp 1 to 4. So if you change the dip switches, it could become 4 to 8, etc. So that's how they get around that problem. So you can do the colour lights. They also have little servo motors in the lamp units to make them move mirrors and all sorts of things, and move themselves around as well. It's just controlled by the 8-bit data sent out.
It's really changed all the lighting scene, hasn't it? By the time you just have big switches.
There are MIDI to DMX devices as well, so in the MIDI sound file you can put your lights in as well, and it will then take one of the channels to sync it to the music. So they're still using this serial Pi module, or Pi serial module. Right.
seems to me this has got some commercial possibilities, hasn't it?
Which bit?
Well, the whole thing. Somebody could make a cheap, using a Raspberry Pi and no gadgets.
Yeah, but these are normal standard
Yes.
devices.
Yes, so it would be extremely cheap then, wouldn't it?
Yeah. Well, as you can see from these, there's only maybe 1 or 2 chips on these.
Yeah.
Another method of controlling is via the internet. So I've got a server here, a server, which is again a microchip. Wait a minute, picture. A microchip computer. So that's what's inside the little box. It's got a network, cable, power. The square chip in the middle is actually the microchip. And it's an 18F67. It's got a built-in network port. It's got GPIOs on the socket on the top. It's got serial port, GPIOs, it's got analog ports. And it's got a 1 meg EEPROM memory chip on it as well, which actually holds the website stuff. But that's an external chip. But it's only a 4-pin chip, and then that little chip down there. That was the RS232 driver. Right. So from the browser, connect to it. That's what you get. That's the start web page. Unfortunately, it's full of Java, so it won't work. The button should be changing, because there's a little button in here, which is just the GPIOs. The LEDs, you can click on them and change them, but there's only one LED in here. The other one's actually connected to the serial port. And there's a potentiometer, which is the little, which is the round red one there, that one there. That's the button. There's another button, but that's the reset button. And there's a thermostat, a thermometer there, a little back bead, which is there. So if we go to the embedded commands, it's a dot here. Right. So this is the same thing, but using the embedded commands that you get with this device. So this time, if I change the potentiometer and put my finger on the button and reload it, then you'll see that the buttons, the last button in the chain says down now because I've got my finger on it, and the potentiometer's changed and the temperature's changed. So if I change the pot again and just do a reload, I've taken my finger off now, so it's gone up. So you can then control things, GPI things, remotely via the network. And so it's embedded commands, so in your web page you put a special command and it goes away and runs a program in the computer which can do whatever you want. So in this case it will return with either up or down if it's a button, or a number if it's a potentiometer. There's another way to connect to it, using Telnet. So you can log in using Telnet. and it tells you it's admin. Just spelt it wrong. And the program that's there just does the same thing again. If I stick my finger on the button, the button there will go from 1 to 0.
And blank the screen.
We did see it for a second.
Yeah. Always.
While it's coming back.
It's behind you.
Nobody sometime.
Quick answer. So that's just the normal telnet into the device. There's another port that it uses. It's that one. Which is telnet again, but it then connects it to the serial port. So if I plug this white box in again, and yeah, it's seen it. Right, so I can now, via the network to this little box, and then via the V24 to that box. And then via the DMX I can do that stuff. It's actually supposed to be for the DMX. If I put DMX, spelling out, it'll start, it'll light the light again.
Fine. Yeah, I found
Switch on the lights in your house from somewhere outside.
Absolutely. So they're all four of them.
Very good.
So that's actually what I bought this little box for, is to be able to talk to the old computers by the serial port, but from a network.
So how much was that little box?
It's not available anymore.
That's a shame.
It was about 35, I think.
No, not bad then.
No. It's, you get the program, it's all written in C, unfortunately. That's another slight problem, I don't understand C. So you can upload the web pages. You've got the source code in C, so you can adapt it, and I've had a play with it and try and get it to do things. But, so it does actually work. So there's a little socket inside it, the white one, which is down there, which you plug your controller in and you can reprogram it. Right, USB. found this little program here, which was by X80 in the Netherlands. Or Rivers there. And that can display what's going on in your USB stuff. Click on the status window, which is a better window. And click on full information. You can see what you've got connected to the Raspberry Pi USB ports. So I've got a powered hub driving the keyboard, which is that one there. It's on external power. And then there must be two internal hubs within the Raspberry Pi. So there's a mouse on USB port 4. If I double click on it, you get more information. It tells you what sort of class it is. Got a keyboard, which is there. And the last one is the network port, which is built in. Right, I've got a USB device here. This is a Bellman 8055 kit. Again, it's a microcontroller there. No. It's a microcontroller, but this time it's got a built-in USB port. It's got that on GPIOs, ins and outs, and analog to digital converters and all that of it. All in the one chip there. Right, so we plug that in to the USB, and then the screen will change. You've seen it, there it goes. We've now got an extra device on the end on USB 7. It's telling me it's consuming 100 milliamps because it's self-powered by the USB. It's set up as a human interface device, although nobody really knows why. But that's what it is. It's got two buffers, two endpoints rather. All the devices have endpoints, these are called endpoints. There's one going out and one coming in this case. If we look at the mouse, there's just one coming in, nothing being sent. They are buffers. They appear as buffers in the Raspberry Pi, so you can actually connect to them and put data into them. Right. There's a little program here, written by Dave Hinton, so that you can there's a set of LEDs there. The top 8 are 8 outputs, and you can click on those to turn them on. Let's just turn those two off. And you can turn them off. These are digital output ports, which are the bottom 2 LEDs, so you can change the brightness of those. And then on this side you've got the inputs. You've got 5 buttons, so if I press the button, the bottom line will change. You see the information has changed as well as it comes in, because that's showing you the information coming down the port. And then there's 2 pots there, under there. Can't see it. So if I adjust that, then that analog one will change. The same with the other one.
Yeah.
Put some notes in here, because it's a bit hard to work out what's going on. This particular device needs 8 bytes to be sent to it for it to work, and then you receive 8 bytes, which is why there's an 800 under these numbers here. And he's got it there. It returns on the receiver every 8 milliseconds, but that seems to suggest it's 1 millisecond, but I don't know. Because it's continually pulling, as you can see from the display when you change the analog. The Raspberry Pi is always polling the remote end, because it's the master. The other end never sends anything, it always has to be polled. Right. So the important things here are this USB number in the box 7 and the end port numbers. It looks like they're both 1 with a knot. One's got bit 8 set. If you click on, there's more information. If you click on the device and then the details, you can get more information. This has all been pulled from the USB. Got the manufacturer and the product. All the devices have a manufacturer's ID, which is this number here, and this number. So the other important thing is you need to send 8 bits, 8 bytes of data out for it to respond. Right. No, that's not it. So again, if you can write a little basic program. So I've inputted the USB address number, which is one of the important things you want. I'll show you this later as it appears in the machine. If I do it now, it'll have to reset it completely. So I'll show you this later. That's the name of the device that you're going to try and open. It's the endpoint number 1. It's the USB, and it's the USB, it'll be number 7 in this case, because it's when I input it, it'll be number 7. So you're opening for output that device. If it's found it, then we're going to continue. Then I'm going to put 8 bytes into the buffer and send it out down the USB. When you put it in the buffer at the Raspberry Pi end, when it's got 8 in this case, the 8 bits will be sent and it will appear at the other end in the buffer. So you actually don't see anything that's going on in the USB at all. To us, it's the other end, it's a buffer. It appears in a buffer at the other end, or a set of memory slots at the other end. And then that's to turn it on, and then to turn the thing off. It's just the same again. Right, so if I run this program, put in address 7. Right. His program doesn't always let go of the flipping endpoint, annoyingly. So if we close the endpoints. So it's lit. All the lights, all the LED outputs are lit. They'll all go off. So again, with a little basic program, you can do that. Right, I've got another little demo here, which is using connecting to this device. If I give it some more power to drive these brighter LEDs. Right. can now control it all from this end. The buttons are being monitored by the program, and then it will send back whatever I need to do. So I'll press that button there, and it will light up that LED. Press it again, it will swap to the next one, etc. Press the bottom button, it will go back. Press that button, it will go on the sequence. So I've got to keep pressing it. Change the pattern. Nowadays, the DMX lights are all these LED displays these days.
It keeps your room cooler as well, doesn't it? It's much more efficient.
Oh, they are. This is using next to nothing compared with the 50-watt bulbs over there.
Yeah, but that's what's happening. Now getting towards proper stage light brightness, aren't they?
Oh, absolutely. These are the ones I use because I had to repair one and this is what left over.
Right, yeah.
So if I change the brightness again, then it should dim down. Should be able to change the brightness by adjusting these pots.
Rock, helping you with Acorn and Riscos computing.